All right, welcome to the final lecture in the Julia course. Today we'll talk about everything that is related to control. And it will be a mix of different things. So we will have some demo of the control system package and related packages, and we will have some demo of ModelingToolkit, how we can use that for control. We will also talk very briefly about code generation. So that's taking Julia code and generating some other code, right? It might be C or it might be just native code. And then we'll very briefly talk about how we can control hardware, maybe in the laboratory rooms with the students when they do labs. So here is a map briefly of the control landscape in Julia. So this is non-exhaustive. There are certainly other packages as well, but these are some of the perhaps more interesting packages. So we have one organization, Julia Control, and lots of people from this department historically have been involved in this. So Albin currently is still here, but also Matthias Felt and Olof Troeng since before, and me. And within this organization, we have the control system package. That is kind of a heavy package that includes a lot of things. This would be very similar to Matlab control system toolbox. So here you find the transfer functions and state space objects and body plots and Nyquist and all of that stuff, right? But very often we can make use of the control system base package, which is considerably more lightweight. The only difference here is that this full package, if you use this, you have access to continuous time simulation. So if you call LSIM or STEP with a continuous time system, that will be simulated in continuous time if you use this. If you use this package, you can still simulate stuff, but in discrete time then. And all body plots and frequency domain stuff, and that is here. So very often you can just make use of this. And the reason they are split up is because this loads much faster than this. The ODE simulators are very heavyweight and take a long time to load. So if you can make use of this package only, don't even bother installing this if you're not going to use continuous time simulation. Because as soon as you install this package, it will pre-compile the differential equation packages, and that takes a long time. So yeah, try to use that. If you want to do H-infinity control or a more advanced LQG control, maybe uncertainty modeling, so using the M-delta framework, if you have taken robust control, you might be familiar with that. All of that stuff belongs in this package. There are facilities for modeling that kind of uncertain systems and solve H-infinity problems. We have a package for system identification, so that think similar to system identification toolbox, where you find the prediction error method, arcs estimation, subspace-based identification, all of that stuff. Exclusively linear estimation, linear time dynamics. We have some facilities to model and simulate nonlinear systems here. So in particular, we allow you to model a system like this, where you have some output, Z, and you have some input, W, and then you have some feedback connection with a nonlinear, static nonlinearity here. If you can express your system like that, we can express it and simulate here in control systems. So a lot of interesting nonlinear systems can be modeled this way. So friction, saturation on the control signal, those kind of static nonlinearities are quite easy to model in this framework. But if you have arbitrarily complex, in particular if you have vector valued nonlinearities and so on, then ModelingToolkit is probably a better choice. All right, we have a package, discrete PIDs, that just implements not just the textbook implementation, but the proper textbook implementation from you find it in the course on real-time systems. So with the integrator, anti-wind-up, and bumpless transfer and all that stuff. That is useful if you're going to actually control some hardware in practice. Then we have the SciML ecosystem, and that is of course enormous. It has a ton of packages. Some interesting for control people are listed here. So we have the differential equations package. That's also an umbrella package. It re-exports a ton of smaller packages. If you're just gonna simulate ODEs or DAEs, you don't even need to bother loading this package. Just load the package that is called ordinary DFQ. So that is more lighter weight. The only reason some people load this package is because then you get automatic solver choices. So if you just call solve on a problem without specifying the solver, this package will choose an appropriate solver for you based on some heuristics. But if you know that I want to use like the equivalent of ODE 4.5, then just load the lighter package ordinary DFQ and specify that you want to use the integrator TC5, it's called in Julia. All right, and this package or the sub-packages here are used underneath the hood when you use ModelingToolkit. So ModelingToolkit is a modeling language similar to Modelica, a causal. I've spoken about it in the modeling course for those of you who took that course. We will show a demo on ModelingToolkit today. That is very useful for control, in particular if you want to model your plant, but you can also model stuff like your controller. And right now we don't have very good support for hybrid continuous and discrete time systems, but that is upcoming. Hopefully the following month will be spent implementing that stuff. And the ModelingToolkit underneath it has a ModelingToolkit standard library. This is just an abbreviation. That includes components for component-based modeling. So if you want to model an electrical circuit, this library has resistors and capacitors and inductors and stuff like that. There's also a mechanical library for translational and rotational mechanical systems. There is currently not a 3D multibody library. That is upcoming, but it will take quite some time, I think. There is a 2D multibody library. 2D is significantly easier when it comes to multibody than 3D is. And then I mentioned here there is a large ecosystem of reachability analysis features within the Julia Reach organization. So all of these top second level boxes are GitHub organizations that include several different packages within. And reachability analysis deals with so you have a nonlinear system and you are uncertain about certain parameters, for instance, but you know they belong to a set. And you are uncertain about the initial condition, you just know that it belongs to a set. Reachability analysis will perform set propagation through the dynamics, so you can simulate kind of set valued dynamics. And it allows you to say stuff like, I can guarantee that no matter what my parameters are within this set, I will never reach a state that overlaps with some dangerous region. So for instance, I guarantee that the robot will not crash into the wall, stuff like that. So that's a way of performing non-linear verification of the control systems. And there are several different packages underneath there that you might be interested in checking out. I also list a few others here. There is an ecosystem of differentiable simulators for robotics called, the main package is called Dojo, but there are several other packages underneath there. There are lots of packages for optimal control. So one of them is trajectory optimization, which is quite sophisticated and is seeing a lot of attention by a group. I think they are at Stanford Robotics. I might be wrong though. We have some state estimation library. It's called low-level particle filters, but there are unscented Kalman filters and regular Kalman filters and all that stuff as well. And then there is, this is currently what I'm working on, Julia Sim Control. That's proprietary, but if you would like to try it, I can probably fix you a license. That has model predictive control and some LMI-based methods for robust control. And it kind of builds on top of all of this and adds extra features on top of that. All right. So Julia Control. Julia Control was the left part here with control system library and so Here are some differences if you're used to Matlab control toolbox or maybe Python control toolbox. I just wanted to go through some differences that you might stumble upon in the beginning. So a very trivial one that we use plural for poles and zeros. When you simulate using any of these LSIM step impulse methods, you get arrays that are permuted in memory compared to what you would get from Matlab. I think from Matlab you get time in the first dimension. Here you get time in the last dimension, and the reason is performance and also to be internally consistent. That also applies to frequency responses. You get frequency in the last dimension, and you get output, input, frequency is the layout. The functions is like ARE for algebraic recap the equation. We don't have C or D here, because that's encoding a type in the function name. But in Julia, the type is encoded in the arguments instead. So ARE will automatically dispatch to the correct continuous or discrete version. The same for LQR and Kalman. And we have separated out some of the more advanced features into this robust and optimal control package.
What kind of advanced features?
Just more options. And this package implements a type called LQG, that if you create an LQG problem, you can automatically ask for what is the controller, what is the observer, what is the sensitivity function, plot me the gang of 4, all of that stuff, so you don't have to do all of that manually. If you call any of the simulation functions, you can either extract the results, so here is the state, output, and time, but you can also just accept the result. It's a structure that you can automatically plot. So if you just say result equal LSIM, that result can be plotted. Just say plot result, and then you will get the plot with all the relevant time series. And also in Matlab, if you just call body without any output arguments, it will produce a plot. And I must say that is absolutely terrible design. Because the behavior of this function depends on whether you have named the output arguments. But that doesn't happen here. In fact, you can't even implement that in Julia without macros. So they never plot anything. If you want to plot, you say body plot. Nyquist plot, that's all. All right, so now we start with a demo in a little notebook here. Let's see. Is this large enough? Yep. All right. So in this notebook, I start by loading the control system base package and the plotting package. Pluto UI is just to provide these interactive sliders and other interactive elements in the Pluto notebook. And I load the linear algebra package to get the identity matrix. So this should look familiar to everyone. I create a transfer function, this numerator and denominator polynomials, or the coefficients of those polynomials. And if I add a sample time here, it would be discrete time. So that's basic stuff. If I say body plot of that, I get what you would expect. Nothing strange. This uses the plots package. So you could add any plot arguments here, like maybe you want the color red instead. Wait, I forgot to come up. And then you get red color. So you can style the plot exactly like you would style any other plot using the plot package. You can calculate Nyquist plots, nothing strange there. We can see there is documentation for the Nyquist plot. It has a lot of arguments. You can automatically plot the circles of a constant sensitivity and stuff like that. It can be quite useful to plot such circles sometimes. And the same for complementary sensitivity. And you can select what the critical point is. It defaults to -1, but you can mark another critical point if you have another kind of Nyquist plot. All right. Here is an example that it creates an LQR controller using the most basic interface. So this should look familiar to most people. Sample time, state space matrices, SS function, nothing strange with the sample time, so this is discrete time. Q is a matrix for the LQR problem. And then this R, I have it as a slider here. All right. The LSIM function in Julia accepts either a vector of the control inputs or a function, and that function is a function of state and time, so you can implement state feedback using this. So here the function is just this state feedback, and then I add some disturbance magnitude times, this is a step at time 2.5, right? So if I move this R here a bit, if I increase it, more penalty and control, we see that I reject the disturbance less. And I can change the disturbance magnitude. If I set it to something very small, I have very small disturbance. All right, so nothing strange. It looks similar to what you're familiar with. And here we see that plotting. Once again, I plot manually, and I just say what the label and X label and so on. So this just uses plots. But we can also support the more fancy things. So these coefficients here in this transfer function, we see that right now actually they are integers because I just put integers in here. But they can be of any number type. So here I load this package Monte Carlo measurements, and I say that k is 1 plus minus sigma k, and that sigma k is a slider somewhere down. And the same for the damping and the natural frequency. And then I create the transfer function with this. Now they are kind of uncertain parameters. They're associated with some probability distribution. So we see that the numerator now is 0.9 plus minus 0.014. So there is some uncertainty associated with this system. So we can plot the distributions of the parameters. Yeah, it doesn't look too interesting. But more interestingly, we can ask what is, for instance, what's the DC gain of this system, and plot the density of that. And we see the DC gain has some distribution associated with it. And if I change now the natural frequency, if I make the uncertainty larger there, we see now the uncertainty in the DC gain is also larger. So that can be quite useful. And now I need to bring these sliders with me down because the screen is so zoomed in. We can see what is the largest. So this, the uncertain values are represented by samples. So I can ask what's the extremal samples. The minimum sample was 1 and the largest was 1.18. We can plot the Bode curve of this system, and we see if I increase the uncertainty in the gain, that has the expected result, right? We can change the uncertainty in the damping. All right, I hope that makes sense to you, why it behaves that way.
The uncertainties in your example, are they interval uncertainties or?
No, they are Gaussian.
Gaussian.
You can have any probability distribution. You can also have intervals that are using interval arithmetic. But if you use that, you will typically be extremely conservative. So this is a kind of a Gaussian distribution instead. And here we increase the uncertainty in the natural frequency. All right. We can plot this in a different way. We could also plot the samples themselves. So if I increase the uncertainty in the gain, I think this is now represented by 100 samples. You can select how many samples you have. When I created these uncertain parameters, I used it's a minus plus, right? That creates something I call static particles. They use static arrays, so they are 100 samples long. If you would use plus minus instead, it would use non-static particles, and then the default is 2000 rather than 100. So I use static here because then the plots update a bit faster when I draw the sliders. All right, so you can combine the control system package with other packages from the Julia ecosystem. So Monte Carlo measurements is one such package, but you can put intervals in there. You can differentiate through things using forward, for instance. So when you do that, the transfer functions will have coefficients of dual numbers. And that's perfectly fine. You can differentiate through, say I compute a Bode curve, and I would maybe compute the H2 norm by summing over the frequency response, and then I would have that in my cost function. That is fine. You can do that. So you can tune PID parameters with constraints on the H2 norm quite easily. All right. The next demo is using a modeling toolkit together with the control system package. All right, so unfortunately that picture is very small. It's supposed to say here we start with a modeling toolkit model, so we spend significant effort very often modeling our system, maybe a nonlinear model with components, and we model everything in great detail. But then very often when we want to perform control synthesis, we linearize that model because maybe that's all we know how to design linear control systems. And if we choose to linearize, then we are in the domain of control system package, so that's indicated by blue. We might do some control design here. Maybe we do some verification in linear simulations because that's very fast, and we iterate a bit back and forth. Then we go back, we convert our controller to a modeling toolkit system, and we do nonlinear simulation and verify that it still behaves reasonably well. And if it doesn't, we have to go back. Otherwise, here it says C code. We might generate C code for our controller. And this is supposed to represent a complete control design workflow using modeling toolkit and control systems. And this will be quite a short demo. There is a longer demo on this video. It's probably the one Busse stumbled upon in his YouTube feed. It's from JuliaCon this year. For this demo, I will load a bunch of packages. A modeling toolkit, of course, a control system, Pluto-related packages. I load the ordinary DFQ so I can simulate nonlinear systems. Croaky is the package that produced the block diagram up there. And then I load modeling toolkit standard library. And I load the electrical standard library, the rotational mechanical standard library, and the block standard library. So a block is just a word for stuff that belongs in a block diagram, and a block diagram has arrows, right? So it's a causal components. So things like signal sources, state space systems, PID controllers, all of that belongs in the block library. Then I create the time variable. That will be useful to create variables later on that depend on time. And then now we're gonna model a very basic feedback loop. So we have a controller and a plant. And we'll go into more detail on the plant model here. So we're gonna model a DCPM, so direct current permanent magnet, I think, electrical motor. And the controller is gonna be a PI controller. So I write it here as transfer functions, but in fact there is saturation and stuff in this, so it's not really linear, but never mind. The motor has the following components. It has some voltage source here, so this we can control it. This is what the PI controller controls. There is a resistor, inductor, this EMF, electromotorical force component. And then that drives an inertia, J, through a shaft, and that shaft might have some stiffness associated with it. Yeah, unfortunate language there, but there is maybe some damping also that is not in the model or in the picture. All right, so all of these components in that picture up there have equivalents in the standard library. So we define an electrical ground. We have a voltage. This is what we don't specify the voltage because this is a signal source. We control that signal with the PI controller. Resistor, it has a value, inductor, electromotorical force. So all of these are electrical. This is a mechanical component. It's just kind of the mechanical ground, if you want. The motor is fixed to earth. There is a torque. This is yeah, that's a load. That's a signal source. We can have a load that acts on the motor, so it's like a disturbance. The inertia is the rotating mass and a damper. So this, you can view it as friction, viscous friction. And then when we have constructed all these components, we just connect them. So we say that the fixed mechanical component, the flange of that, is connected to the support flange of the electromotorical force, and that's also connected to the friction flange. All right, so we don't need to go into detail in all these connections, but you see that, for instance, connection of the resistor to the inductor and the inductor to the electromotorical force is exactly these connections here. So it's these lines, essentially. And crucially here, these lines don't have arrows associated with them. This one has an arrow, but it's just to indicate which direction is positive. So this is an acausal model. And the connection statements here, the order in which you list the variables here doesn't matter. All right. We group all the subcomponents into a vector because we need to provide them to this compose. So here we compose all the subcomponents into a model. And that is now our motor component. So next step is to add a PI controller. We will use, it comes from the block library, lim PI for limited PI, so it has anti-wind stuff like that. So now we just instantiate the motor. This is the function we created above. So it creates the system we have just looked at. Here is a disturbance step amplitude, and then we create a signal source. So in Simulink and Modelica, you would drag a block in that says step. So this is that blocks.step. It has a height and stuff. PI controller, nothing strange there. The parameters are given by these, and these are given by sliders, and I think they appear down here, so we can tune the PI controller. Some saturation and tracking time constant for the wind up. Feedback, this is just a feedback node where we add the reference and subtract the measurement. And load step, so this is also a step disturbance, and then there is a speed sensor that converts the mechanical speed to the signal domain. So you can't immediately connect the speed of the rotating inertia to the controller because they live in different domains. The speed is kind of in a mechanical domain, and the PI controller works in a signal domain, a causal domain. The speed sensor will, just like in real life you need something to measure the speed, we add a speed sensor there. And then there is a bunch of other connections. So now we connect, now we are in the block diagram. Now we're no longer inside of the motor, we are now in the block diagram. And here appears something that is of interest to control people. This connection has a symbol here in the middle. So this, you can view it as we add a name to this connection. Formally we add something called an analysis point. And this connection is causal. So the order here matters. If you would put speed sensor.w on the other side and flip it with this, that would mess things up. So if you would calculate the sensitivity function in this point, you would get the complementary sensitivity function instead. So keep that in mind. But this, for now, this just adds a name in the block diagram. This signal is named y. And it's at the output of the speed sensor. Some more connections, and then we have PI controller.control output. This connection is named U, so this is the control signal, and it goes to the motor voltage source there. All right, we can simulate that. Yeah, I'll go back up to the plot when we have looked at the code. Once again, we group all the subcomponents. We package it into a model with a compose function. And then we perform structural simplification. So this call invokes the ModelingToolkit model compiler. So before that, we can try to type that model out. Let's do it here. Model. That's probably a quite large, it didn't even want, yeah, there is an error that when you try to show these signals with names, if we do instead display model, that should work hopefully. Yeah. So this model has 57 equations, and it says 91 if you remove all the aliases. Without any simplification, it's 91 equations. It has 90 states and 25 parameters. This seems ridiculous. There should only be a handful of states max, right? We have a PI controller, it has 1 state, and we have a rotating mass, 2 states. And we have some electrical component, 1 state, right? So this seems messy. But after we have run structural simplify, we get sys. We can write display sys also. All right, it has 4 equations and 4 states. So simplification removes each connect statement that connects 2 components together. So it adds just a linear equation that says this thing is equal to that thing. So all of that can be simplified, and now we have the inductor. The current in the inductor is 1 state. The PI controller integrator.x is 1 state. That makes sense. The model inertia position is 1 state. And the last one is not shown, but it's probably the velocity of the inertia. And some parameters.
This array, it has 9 columns because there are 9 blocks, or
the incidence matrix. Yeah, good question. I think 12, 4 by 9. It should say which equations it should represent.
Yeah, so it's the equations in the rows, but the columns, they are the blocks, or what are the columns?
Yeah,
you connected. How many things did you connect? Was it 9?
We can see how many components we have made.
2, 3, 4, 5, 6.
No, I don't think it's the components. I think if we do. Oh. No, okay. I'm not entirely sure. It saves a bunch of things also to reconstruct simplified stuff. I don't know if it's related to that. But I do believe it should represent a bipartite graph that matches equations and variables. But where the 12 comes from, I'm not sure, to be honest.
Okay, so it's 9 variables that are in 4 equations, and there are 12 non-zero entries.
Well, after simplification, there are 4 equations and 4 states, so it doesn't quite make sense. We'll have to ask Jingbo. He's the only one who knows the internals of ModelingToolkit. All right, so we did the simplification, and then we can package the system into an ODE problem. So that's when we want to simulate it. This is the time span from 0 to 6 seconds. And then we solve the problem using RODAS4 integrator. And then we just plot. So this is a bit confusing at times, but we can index the solution using the symbolic parameters. So we plot the x-axis is the time, and the y-axis is we index the solution and we grab motor inertia w. So that's the rotational velocity. And then we plot some other things also. And that's what we get here. So now I'm going to try to, since we zoomed in so much, I'm going to move these sliders here. Can I do that? So we can tune the controller. So we can probably crank up the gain a bit. Yeah. All right. And we see it's kind of sluggish here, the time's constant, so we reduce the integration time slightly. All right, and now that's fast enough, but now the gain may be a bit too high. All right, maybe we're happy there. Who knows? So this quick and easy way to, now we're actually performing, even though the motor is a linear system and the PI controller is actually non-linear, but we can do this interactively, and it's quite quick once you have set it up. So you can use this to tune basic controllers. All right, I will grab those and bring them with me down because I need them later. the next step is to maybe reason a bit more about the robustness. So we saw a time domain simulation, it looked fine. But we should also, before we are happy, we should check maybe the gang of 4. All right, we should probably always do that. So don't bother reading the text. We're going to compute the sensitivity function. And we can do that using the analysis points we have added to the model. So if you remember the connection statements that had a name in the middle. If I call get sensitivity of model in the point y. So if we have the following block diagram, here's a controller, here is the plant, here we have u, here we have y. All right, it looks like this. R. I have named this connection y, so I can say give me the sensitivity function in that point. And now this is a single input, single output, so it would be equivalent to ask for it in this point. But for multiple input, multiple output systems, they are different, right? Output and input sensitivities. So what that will do is it will internally linearize the model. And what will it linearize? It will add this little, inject an input signal here. So it will inject the disturbance there, additive plus. And then it will linearize from here to here. That's the definition of sensitivity function. And then it will compute that linear state space system. It returns a named tuple with matrices, A, B, C, and D. And I package these matrices into the SS command from Control System Toolbox, and then I perform minimal realization there on that. And then I get the sensitivity function, it's this state space object. Yep.
How does it know what the linearization point you want?
Good question. I can provide an operating point here. It's a dictionary that maps each symbol to a variable. If I don't do that, it uses the defaults that are stored when you create the model. So all of these components from the standard library, they have default initial conditions. It will use that if you don't provide anything. So you can override one or many or all, but you can also just not provide any at all. So the default is always typically 0, if 0 makes sense. But yeah, good question. We need to do that in general for a nonlinear system, of course. All right, so now we have a state space object that represents the sensitivity function. These, once again, are just the parameters of the PI controller. We can ask for the H-infinity norm. So the maximum sensitivity is 1.3. Are we happy with that? I don't know, it depends on who you ask. It's not great, not terrible, perhaps. But now we can also plot the sensitivity function here, and I indicate the peak there also, and we can plot the Nyquist curve. So the Nyquist curve, we require the loop transfer function. And there is a similar to get sensitivity, there is also a get loop transfer. And I get the loop transfer in the point u here. But for size of systems, they are equivalent. And then I just, remember this returns a named tuple of the matrices. I just splat that into the SS command. And I have a minus sign here because the loop includes this minus sign here. But we usually don't include it when we plot the Nyquist curve. So if I didn't put minus there, the Nyquist curve would be mirrored in the imaginary axis or rotated like that. All right, what do we create the frequency vector? Bode plot, I say don't plot the phase. And then scatter here, I just add the maximum sensitivity point in the plot. Nyquist plot, okay. MS circles, I draw that circle in the MS I computed with H-infinity norm. And then I group all the plots into one plot, and I create the layout so it looks fancy. And we have all the plots here. And now we should be able to drag the sliders, and we see how all the plots update. Yeah. So if I crank up the gain, we see the maximum peak in the sensitivity function here. It's increased, and we also see that this circle is decreased. So the maximum peak in the sensitivity function, right, is the inverse distance from the critical point to the Nyquist curve, the shortest distance. So we can use this to find a tuning we are happy with. All right, yeah, it doesn't matter. All right, but we can also call linearize ourselves if we want to linearize a model and get the linear system. The interface is slightly more tricky, so you can linearize between two analysis points. You can say linearize the model between u and y. But then you get the linear system between u and y when the loop is closed, because you have closed the loop here. What you can do is you can say open this loop at y. Then you get a new system, and then you can say linearize between u and y. Then you get p, or a linear version of p. But you can also use the more low-level interface where I say, first I call complete motor, that's just to make it easier to refer to variables inside it. Then I say linearize the completed motor, and I want to linearize between the source voltage and another input is the load.flange.tau. So this exposes some internal details, right? The load source has a mechanical flange and that has a torque. So these are my two inputs, and my output is the load flange angle. All right, and then I get the matrices A, B, C, and D of the linear system here. So I can call linearize on any arbitrary model. And under the hood, this uses forward diff. So anything that can be linearized using forward diff will be fine. But there are of course systems that are they are non-differentiable in certain points. If you have friction, Coulomb friction, as discontinuous and so on. If your model calls some function in that is implemented in C, maybe you can't linearize that. Then this will fail. Then you need to do some kind of, you can always do finite difference linearization. You can also do frequency response analysis. So we do that in practice maybe if we want to estimate the model of our system. We send the sinusoidal signals in there or a chirp, something like that. We can do that in simulation also, and that will give us a linear model. So all of that is feasible to do. All right, that was it for this demo. So the next step is to have a short break, and then we will look at controlling hardware. All right, maybe 11:10 we can continue.